As the world around us grows more and more interconnected, and the Internet of Things produces increasing amounts of data about the world around us, we need a way to sort through this unstructured data. In fact, by 2025, we'll be producing 463 exabytes of data every single day. Now, just for context, this is what 463 exabytes looks like in bytes. Keep in mind that this is per day, not even per month or per year. Every single day, we'll be producing this much data. But how do we look through it all? Your initial guess may be to say, supercomputers. Why not? They seem strong. But there's a fundamental problem coming about. You see, as supercomputer chip sizes grow smaller and smaller and smaller, they begin to act in very strange ways. These very strange ways are what we call quantum mechanics. Quantum mechanics is just the physics of subatomic particles. What's cool about quantum mechanics, however, is that we can leverage it to create something that we call quantum computers, as you may have guessed. Now, one thing about quantum computers that they can do much, much better than classical computers, that they can sort through unstructured data way faster. Unstructured data examples in the Internet of Things may include the power production of solar panels, or even words in a randomly generated database. Let's take a look at what this would look like classically. In a classical algorithm, the algorithm would look at each index in the list and tell us if it's the item we're looking for. So for X, it would tell us, okay, is X Y? Assuming that we're searching for Y. Is X Y? No, I move to the next one. The second X. Is X Y? No, still not X. So I move to the next one. Y is Y. Yes, exactly. So it would return the index of Y. Now, this type of algorithm would take us the length of the list and over 2 times or tries to run on average. And in the worst case scenario, which is where Y is at the very end of that list, would take us the length of the list. And once again, that's the worst case scenario. What if I told you that there was a quantum algorithm called Grover's algorithm that could achieve this, that it could find Y in any list, no matter the position of Y in that unstructured data, in just root of n, root of the length of the list. Now, you may be thinking, okay, well, if n is 4, 4 divided by 2 is still 2, and the root of 4 is still 2. So, yeah, I mean, it's pretty much the same as doing it classically, right? Well, let's take a look at this chart. There's always a cool chart for everything. So here we have modeled in red, n over 2 versus the root of n. Now, the root of n may be a little hard to spot at first. It's actually at the very bottom of the screen. It's the one modeled in blue. As you can see, there's a drastic difference in the amount of tries it takes just to get the right index Y. So at 20,000, for example, it would take, at a length of 20,000 rather, it would take around 10,000 tries with the classical algorithm on average. And then with our quantum algorithm, with the quadratic speed up, it only takes something barely more than 0, at least on the scale of this graph. So how would we achieve this? Well, if we think about my chances of guessing the index of Y right in any list, I could guess that, assuming it's an unstructured data, of course. So if I guess that Y is in the first index, that's essentially the same, that has the same amount of being right as Y being the last index or the third index or the fifth index. So no matter what my guess is, it's equally as good as any other guess. So this can be modeled by what we call a superposition, more specifically an equal superposition. So that's exactly what the state S is. It's an equal superposition of all our states. So in this example, we'll be going over a 2-qubit state. So we could either have the 0, 0 state, 0, 1 state, the 1, 0 state, or the 1, 1 state. Once again, we have a normalization factor of 1 over 2, which is our amplitude. Then by the Born rule, we see that our amplitude squared is actually the probability of measuring each state. So each state has a 1/4, 1/2 squared is 1/4 probability of being measured, and this fits our probability since we need our probability to be 1, and 4 times 1/4 is 1. This can be interpreted geometrically by the state W being modeled on the y-axis on the left, which is the state that we're looking for, and our S being modeled in our state S being modeled in the purple. And we'll say that we have a state S called psi0 that we'll use for the purposes of our geometric interpretation. And this S prime is not that hard to calculate. It's just S minus the state of W. So it's a state in which it's a state S in which we have no probability of W. So it would look something like the top with only the 0, 0 state, the 0, 1 state, and the 1, 0 state, since we have no probability of measuring W once again. And we define this interior angle between S and S prime as theta. Now let's look at the amplitude. Once again, every state has an equal amplitude, as you can see here. 1/2 is applied to every state, and then 1/4 is the probability of it being measured. So it's an equal superposition, and we can see the amplitudes there. And our W has the same probability of being measured as everything else, and our W is in purple, as you can see. Now, we need to define something called an oracle. Now, the function of this oracle is we give it a certain state that we want to measure, right? So it could be any of the states 0, 0, 0, 1, 1, 0, 1, 1, and we say, okay, mark it somehow. So what the oracle actually does is that it gives a negative phase to the state that we want it to mark. So that can be visualized here in psi t prime. So it's a superposition. You can see that with 1/4 chance of each 1/4 probability of each state being measured. So 0, 0 has a positive phase. Once again, 0, 1 has a positive phase. 1, 0 has a positive phase. And we see that this 1, 1 state has been marked by a negative phase. And that's the beauty behind Grover's algorithm, so we mark this phase somehow. And yeah, so we have a negative phase that's only applied to the 1, 1 state. So we only want the negative phase to be on the very specific state that we want to mark, where our oracle function does not touch anything else, as we can see. And this can be interpreted geometrically. Once again, state W, state S still there, state S prime. And then we see this U omega, which is our oracle, acting on the psi t state, of which we said, once again, was an S state. So U omega acting on psi t gives us this new psi t prime, which we see at the top. And this corresponds to a reflection of this psi t t0 state, or the S state, around the S prime state by a factor of theta, once again, because this interior angle between S and S prime is theta. Good progress. Let's look at the amplitude implications. Once again, we know that our negative phase will obviously give a negative amplitude to this state W, and this will lower the average amplitude of the entire superposition, which is marked by the dashed line. Next, we define a diffuser function, and this is the last step in Grover's algorithm. It's somewhat arbitrarily defined as this unitary S is equal to 2 times the outer product of S minus the identity. This may be a little bit hard to understand what's actually doing, but it's nice that it has a geometric interpretation. So we take our original U omega phi t state that we had down here. Remember, it was below the S prime. And this operator, the diffuser, reflects it around the equal superposition, the S state. And it does so by a factor of 2 theta. So it reflects this unitary omega phi t state about this equal superposition state by 2 theta. Once again, because theta of S between S and S prime and phi t was 2 theta. So the total rotation back around would be 2 theta once again. Yeah, so we can see that this doesn't fully take this equal superposition to state W. But what's really interesting about this is that running experiments, we can see that the average amount of times that we need to repeat, once again, the oracle step and the diffuser step is root of the length of the list. So in our case, we will only need to run it once, and we will get to this state. As we can see, it's not exactly W, but most of the time, once again, we run multiple quantum simulations. Most of the time, it will collapse when we measure it into this into the state W. So once again, most of the time, a majority of the time, clear majority of the time, it will collapse into the state W where we can measure it easily. Now that we've gone over this, let's take a look at what it's like to code in Qiskit. I'll see you there. So here we are in the 2-qubit example. We'll import some useful libraries like matplotlib, pyplots to visualize, and numpy, just useful in general, as well as all the Qiskit libraries that we will use within our code. Okay, so we set our provider. So this is something that you do if you want to run your code on an actual quantum computer. So if you go through IBM Q, that's how you'll do it. We define our number of qubits, so in this case 2, and then our Grover circuit as a quantum circuit with an equal number of classical bits and quantum bits, qubits. So in for each of our qubits in the quantum computer, we in the algorithm rather, we will apply Hadamard. So once again, this is our initialization, as covered earlier in the video. We initialize the circuits, draw a barrier, and then draw them. So this is what it would look like, where each of our qubits has a Hadamard applied, and then this barrier is just for visualization purposes once we start making more complex circuits. Once again, we initialize the circuit to an equal superposition by applying Hadamard gates to both qubits. Here we will define our oracle for the 1-1 state using control Z gate. So we have the control as 0 and the target as 1. Once again, we have the barrier and we draw the circuit. So this is what control Z looks like. And then lastly, we will define our diffuser, which is a series of H's, Hadamards, followed by Z gates, followed by a control Z, and more Hadamards. And then we will measure the circuit to 2 classical bits, which we can see at the bottom, and that ends after this barrier over here. So this looks like this in Qiskit. So we apply an H gate to each of the qubits, and we apply a Z gate much the same way. We will create a control Z where 0 is our control and 1 is our target. We will once again apply the Hadamards in the same way as up here, draw the barrier, we measure them, and then we draw the circuit. Okay, so this is how we run our circuits on a Qiskit simulator called QASM simulator, which is essentially supposed to serve as kind of a quantum simulator. We find our job executes. So we define our backend as a QASM simulator. We create a job, we execute the job with only one shot, which means we will only run the simulation once. We get the result of the job, we get the counts, and we print the counts. So here we can see that 100% of the time, the one time that we ran it, we got the output state 1-1, which is the state that we were looking for. So when we run our circuit on a quantum simulator once, we get the 1-1 state that we were expecting. So now let's see what this is like to run on a real quantum computer. So we define a device, and essentially this least busy will find a quantum computer in IBM Q's network that matches our filters. So here we're looking for a quantum computer that has 3 or more qubits, and it's not a simulator and is operational. So we print that device and we find that it's IBM Keto. Once again, this may be different when you're doing it. Might be IBM QLM or another device. This code will find the least busy quantum computer in IBM's network and prints the result, as we can see. We will transpile the Grover circuit. Essentially, this is just the device. You want to run it on the circuits and the optimization level. So the higher you set this optimization level, the longer it will take to run. We set a job to run on this device, and we will monitor the job, which essentially prints this status every interval of 2. I think in this case it's 2 minutes. So job status, job has successfully run. So this will look like something waiting in line, or running a job on a quantum computer. I think this total code took me 10-15 minutes to run, so not too bad. Again, as you set this optimization level higher, it will take slightly longer to run. Yeah, this code will run the job on the quantum computer and keep track of the status. We'll see it here. We get the results from this job. We get the counts of the job, and then we plot the histogram. And as we can see, the highest probability here is our 1-1 state with an 81% chance, outputting 1-1 81% of the time. And the other possibilities are just false while running the quantum computation. So as we can see here, they're significantly less than the actual state. So now that we covered 2 qubits, let's see what it's like on 3 qubits. Okay, here we are in the 3-qubit example. Once again, we have the exact same imports as last time. And this time we'll solve Grover's algorithm on 3 qubits with 2 possible solutions. So, we define this initialization function, which applies Hadamard's to each of the qubits. We will create an oracle function that will look for 2 specific states. So in this case, 101 and 110. We will apply a controlled Z with a control of 0 and a target of 2, which will look for this state, and a controlled Z with a control of 1 and a target of 2, which will look for this state. We will define this oracle as a gate and call it the unitary omega, which is the standard notation that we use for oracles. Once again, we will apply this diffuser function. This is a general diffuser function that will work on any number of qubits passed in. So it doesn't matter the number of qubits, it will work for any case. So in this case, it will be 3. We defined a new quantum computer. So once again, we apply H's to all of our qubits, which will take them out of superposition. We will apply X gates to all of them, which will take them to the 1 state. And we will apply a multi-controlled Z, and we will apply another multi-control to fully, targeting this last qubit. We will reverse what we did over here, and then once again reverse our X's and reverse our Hadamards. And then this will produce that rotation that we were talking about earlier, which was the 2 times the outer product of the S's minus the N. We will take this diffuser function to a gate, which we'll call the unitary S, which is the standard notation for a diffuser function. Once again, we define a general diffuser function that will work for any number of qubits passed in. Next, all we need to do is append these functions to our Grover circuit. So as you can see, we initialize the circuit, we append the oracle, we append the diffuser, and we measure them and we draw. So this is what it looks like when drawn. Once again, we get the initialization with the Hadamards, the oracle with U omega, and the diffuser with U of S. Remember that this is one of the special states as well, special cases rather, where we only need to run through Grover's algorithm once. And we apply the measurements to each of our qubits to take them to 3 classical bits. All of this code looks much the same as from the first example with 2 qubits, except here this histogram count, we only have 101 and 110, which is slightly more than 47% for 101 and slightly more than 52% for the 110 state. And this occurs, ideally, this should be a 50-50 distribution due to the probabilistic nature of quantum mechanics. These states will likely never be equally 50-50. So again, we load our count as much the same as from the last example. Once again, we find the least busy quantum computer according to these specifications and we print the device. So in our case, we have IBM QLM. We transpile our Grover circuit once again, which we just given an optimization level, same as the last one for 3. We run that job on the device and we monitor the job status, job has successfully run. I think this example took me 20 to 25 minutes. So I think the IBM network was just a little bit more busy. We get the results from this job. We plot the histogram. Once again, we can see two major outliers, 101 and 110. Once again, this is just, the rest is just to the probabilistic nature of quantum computation. If you enjoyed this video, be sure to smash that subscribe button and the like button down below. If you're interested in learning more on Grover's algorithm, the link to my article on this topic will be down in the description. If you have any further questions, feel free to contact me. My LinkedIn, my Twitter, and my email will be down in the description below. That's it from me today. Until the next video, peace out.